warahmatullahi wabarakatuh. Salam sejahtera. Good afternoon, video. Okay, now we're going to continue with our second topic towards thermodynamics, JIS 314. So the topics of energy transfer, and energy analysis based on your textbook. Okay, part of that, some of the subtopics we're going to have various forms of energy transfer by work, and so sorry about that. And okay, so to have a look on the first law of thermodynamics and also energy conversion efficiencies. Okay, so we'll focus more on the form energy transfer by work and heat, and also first law of thermodynamics. Okay, I have to move it here. Okay. No. Very okay, so it's the heat transfer and everything. So let's say you're going to have a refrigerator. Just don't look at this area, just look at this particular side. Okay, pointer. Okay, so we're going to have a clear and well insulated room. Which has an adiabatic closed system in that room. So is not coming in, or the energy is not coming out of that room. Okay, so what is your expectation when you have a refrigerator and an open refrigerator? Definitely you say, okay, the room will be literally means partially going to reduce the amount of temperature in that particular room. So, but we forget something. The energy interaction involving the refrigerator and also the electrical energy crossing the system boundaries. So means for it to have a cooling system, okay, only that's going to have some work being done on the compressor behind here. So the amount of heat going to be released. So basically, you're going to have a heat transfer in this refrigerator system, but at the same time the room temperature will also rise due to that. We need to consider the whole system. That's why this is a refrigerator in an insulated room, so it is a system in a system right now. So basically, what we're going to see right now is towards the heat transfer and energy transfer. So that. Okay. Now we have different kind of energy. Okay, we have electrical, magnetic, chemical, nuclear, mechanical, so on, and etc. We are more interested in the total energy of a system. Okay, where thermodynamics focus on change of the total energy. We're going to have two categories of towards this energy. One is microscopic, the other one is macroscopic. Okay, so the macroscopic, you're going to have kinetic and potential energy. Means we're going to have kinetic energy in motion relative to some reference frame. Okay, have, and then the potential energy is towards the system which result to of the elevation and gravitational field. So you're going to include the gravitational acceleration and also the height, and which is focusing on. So besides that, towards microscopic, you're going to have molecular structure of this system. Okay, so which in previous in first chapter we discussed about the internal energy which is with the kinetic energy as well, which due to the particle. Okay, so that's why for the microscopic is more towards the molecular structure of the system. The degree of molecular activity, how the movement, how fast it goes. Okay, basically, okay, on here. Oh, okay. Okay. The total energy of system on the unit mass basis is denoted by italic E. Because, even though we are focusing on the capital E as the total energy, when it is unit mass you see the dimension will be changed towards the total energy on a unit mass basis. So that's why you're going to have here E equal to M. So total energy, suppose you're going the dimension will be kilojoules. So you're going to have kinetic energy. As we know, the kinetic energy we have multiple velocity of 2 over 2. So you're going to kinetic energy. But when the dimension we're going to have a load on the kinetic energy per unit mass, then we divide with M. So remove M. So we're going to have V power of 2 over 2. So it goes on with the potential energy, where it considers now, as I said, the gravitational acceleration and also elevation of the center of gravity system. So depends on which is the reference level that we're going to have. Okay, so basically when you have the E is actually the specific stored energy. Well, sometimes certain books saying that they're going to calculate on the specific stored energy. So this is what they are looking for, but it depends on the per unit mass or the total that we don't, I mean, sometimes we just consider the mass as a constant value. Okay, and for you, the total energy of one particular system in kilojoule, the dimension will be in kilojoule. So you're going to have E equivalent to plus kinetic energy plus potential energy, and Q is the internal energy. Okay, it's the internal energy. So basically, let me move that. Oh, okay. Sorry. No. And here, the stored energy of one particular system consists of change in the internal energy, and the kinetic energy, and also the potential energy. Okay, that's what you need to understand first. Okay. Now, most systems remain stationary during the process. So that's why I said initially thermodynamics is more focused on the classical theory, but we go with the efficiency level and everything, so we need to consider most of the particles that move freely, and where you the kinetic parts. So that's when you use system, so you're going to have no changes to kinetic and potential. So when you have no changes, it's just that the changes of the total energy is equivalent to changes in the internal energy. This occur when you have a really closed system. When you heat up externally, okay, so you actually heat the inner well. Okay, for the sorry. Okay. So under the control volume, when you have a closed system, you're also going to have a closed control volume. Okay, so typically it involves fluid and gases. Okay, for a certain period of time. You can see our refrigerator system. You can see it's associated with the fluid, the flow of the fluid in the system. Okay, so it is means actually in a rate form. Okay, let's say this is the control volume, fluid flow. So we're going to have certain diameters for that, and the stream towards the from left to right. So now we have identified the amount of mass flow through the cross system per unit time. Okay, so basically amount of mass flowing through the cross section per unit time, because the time is moving. Like when the flow is there, the time is moving from one end towards the other end. Okay, so we know that the mass flow rate, okay, Okay, because firstly we have what we know is okay, we have rho, okay, equivalent to over V. So since right now we are considering the volume that goes towards here, that's why we changing, okay, so we are considering the flow, okay, equal to V, the dot there. So dot throughout our discussion for this sorry, not only for this chapter, for coming chapters and so on until we finish this topics on thermodynamics. So we're going to have the dot symbol used to indicate the time rate. Okay, so the amount of mass flowing through this control volume, we're going to have two. This is mass flow rate, and the other one is the energy flow rate. Okay, so now there are also some physical insight towards the internal energy, as you can see. For this form of microscopic energy under the sensible energy, because sensible energy is a portion of internal energy system associated with the molecules, energy of the molecules. So you for the molecules, like we used to know that you're going to have translation process, you're going to have rotation process, vibration. Okay, due to that, you're going to have internal energy of the molecule. Okay. Not only that, we're going to have also latent energy, which is associated with the phase of the system. Okay, the system, it can be from a solid becoming a liquid, becoming a vapor. So those two, you're going to have the thermal energy. Okay, so with that, we're going to have also chemical energy and also nuclear energy. Okay, so which relate with the atomic bonding for the chemical energy, and also for the nuclear energy is the binding energy of two atoms, okay, or molecules. Okay, so it relate with that. Now, we have a look also on the mechanical energy. Okay, the mechanical energy, the form of energy that can be converted into mechanical work. So our right now is towards the energy, the work being done, because when we discuss about heat transfer, the energy transfer, it relates also with the mechanical energy and also the kinetic potential energy, because it some of the parts that we're going to deal with is actually the mechanical devices, just turbine and also pump. Okay, under the kinetic and potential energy, the familiar form of energy will be, okay, so make energy of a flowing fluid per minute mass. So you're going to have the kinetic and also the internal mechanical. Okay, so the mechanical energy of the flowing fluid will be you can see the dot there, right? Okay, so that is when we multiply with the mass of the unit for them. Okay, so now, but when we hit a constant for the flow unit mass, normally the fluid, let's say we're going to have a constant density. Okay, when you have a constant density, then during the fluid compressible flow, so we're going to have the 2 minus P1, so you're going to have different for that. Okay, now, sorry, but so for the mechanical energy will also definitely change. We're going to have different towards the V and P. Okay, now for energy transport, heat and flow, sorry, and the classical sign conversion. Now, they need to verify this clearly. Okay, between heat and work. Okay, and may cross the boundary closed system only by heat or work. Okay? There's two parts. You're going to have heat crossing towards the boundary or work. Okay, so okay, have heat. I can also ask, what is heat actually? So heat is energy transfer across a system boundary. So your system boundary is an energy transfer due to the temperature difference between system and its surrounding. Okay. So you're going to have equilibrium between when going to have a two temperature difference. So so energy transfer across a system boundary can be thought of as the energy expended to lift a weight. It's called a work. Okay. So energy transferred to the system, so it moves something. Okay, force there, so that's what you call work. So you have heat and work, two most important energy transport mechanism between them and the surrounding. So it's really important. Please understand. Okay. The shift between heat and work, both are nice as boundary system across the base. Okay, both are best energy. Okay, the system possess energy, but not towards heat or work itself, but the heat and work is the energy towards the system. Okay, so both have function and we have magnitude. Okay, so when I magnitude, still refer to the chapter 1 that we discussed. You're going to have Q in, Q out, W in and W out. Okay, we're going to have positive, negative function over there. So we're going to have a look. In. So towards energy transfer by heat. So the form of energy that is transferred between two systems. So the heat going in and out of the closed system. So this is the system boundary where the mass is constant. So you're going to have work also transferred towards the system. Okay. Let's say now you're going to have the room temperature will be 25. Here is an example. And the second, the internal part is 25 degrees Celsius. There will be no heat transfer. But let's say you have 15 degrees Celsius or 5 degrees Celsius difference with the room temperature, so you're going to have heat transfer towards it. Because the higher temperature will go towards the lower temperature in order to have an equilibrium temperature. Okay. Since heat and work are path dependent function, so actually you're going to have kind of heat and work towards both paths. Okay. Now bear in mind, although we have this integration function, okay, it does not mean when we have towards the delta Q, it does not mean Q is Q2. No. Q1 is Q2 Q1. Okay, so it is along the path from Q2 Q1 or Q1 Q2. Okay, it identifies the amount of heat or work that is transferred in the system or out of the system. So now, a point function that you're going to have is actually you're going to have it here now. So let's say from point 1 to point 2. So the transfer of means the work that being done from point 1 to point 2 is actually the integral of W1 W12. Okay, as you can see the slide. Okay, so this is what matters. Okay, so the sign convection is required for heat and flow that and work energy transfer is actually a classical thermodynamic sign convention. So we have discussed about this. What I mean, okay. So we have a closed system, okay. You have the surrounding, so the heat is coming in, the work is coming in, or the heat coming out. So you need to have the sign, the classical thermodynamic sign convention. Okay. So this will be a guide for towards the magnitude. When we do the calculation, we have certain value. Sometimes value is going to be positive, sometimes value going to be negative. So that is going to have a significance to that. So we're going to find out later on. Have a look. Okay. So it's the same thing. So towards the energy transport by heat. Okay. It is the transition between the boundary due to the temperature difference. Okay. So it's going to a stage of equilibrium. So the net heat transfer to a system is actually the total heat in minus the total heat out. So if it is in equilibrium, definitely going to equivalent to 0. Okay. So in most thermodynamic types, the quantity Q means to be the net transfer to the system of Q means Q net. Okay. The heat transfer also measure in joules. Okay, it also measure in joules, and you're going to have energy per unit mass. That's why you're going to have small to Q. Okay, so when you have a per unit mass, so it's to change the dimension totally. Okay. And yeah, additional part here. Okay, the adiabatic process is one in system is perfectly insulated, and the heat transfer is 0. Okay, the heat transfer, because in chapter, if I'm not mistaken, chapter 3 and chapter 4, we're going to discuss more towards the adiabatic process, isochoric process. And so the adiabatic process is the perfect system. Okay, so that's it. Okay. Now we have a look on the conduction, convection, and also radiation. So we're going to discuss a bit also in this part. Okay, under the heat energy transfer. So conduction through plane walls. Okay, so heat transfer is a progressive change of energy between the molecules of a substance. You have a collar, you have air surrounding. So this is the system. Heat, the surrounding temperature is higher than the collar itself. Collar can. Now, when we go towards the macroscopic level here, okay, we can see the air boundaries, and so the collar is really going for a wall of aluminium can with certain thickness that is delta X, and of the temperature we have is delta T. Means when you have a conduction, okay, the law of heat conduction, okay. Okay, in the equation, don't worry, it's given. Okay, so to have the transfer for the conduction is negative A kT differential of temperature towards the thickness of the boundaries. Okay, so basically you're going to have the heat flow per time. You have the thermal conductivity. For every material, we're going to have different thermal conductivity values. So I'm going to give to you, okay, in our e-learning, okay, towards the thermal conductivity values for different materials, okay, and normal to heat flow, okay. We have it here. Normal to heat flow is the area. And so the temperature gradient. So when you have the temperature gradient, the dT over dx towards the heat production. So what is the thickness that you have? Now, basically, when we perform the integration, okay, let's say we perform the integration towards here, so we need to have kTA delta T over delta X. Okay, so the integration is the series. Okay, the series. Okay. So now when we have a look back, T higher than T1. Heat flow from right to left. Okay, so in order for it to have a thermal equilibrium, okay, so we have this. Okay, for example, yeah, okay, now let's start to the equation part. Okay, let's say that wall is composed of 20 centimeters of bricks having a thermal conductivity KT equivalent to 0.2. Okay, sorry, 0.72. The right phase temperature of this brick is 900 degrees Celsius, and the left phase temperature of this brick is 20 degrees Celsius. So you need to determine the rate heat conduction through the wall per unit area of wall. Okay, firstly, you can identify, so there's a temperature gradient, so the thickness of 20 centimeters. So so for any calculation that you run, you perform, or you compute, so you need to have a, what you call it, SR to be, okay, so for this 20 centimeters is equivalent to 0.2 meter. Okay, basically based on the formation, okay, so the Fourier means integration of Fourier, okay, so to find what is the rate of conduction, okay, so basically rate of heat conduction Q dot, okay, over equivalent to area through, okay, through wall per unit area. Okay, rate of conduction through the wall per unit area means you're going to have the Q dot over A. Okay, so what you need to find. So basically delta T is 900 minus 20, the what do you call it, thermal conductivity, sorry, thermal conductivity is 0.72, and you have delta X 0.2 meter. Okay, so basically the rate, okay, is around 168. So and this was to be in the other slides. So action heat transfer is the mode of energy transfer between the solid surface and adjacent liquid gas in the motion. Basically, you have, okay, have a look at this rather than this diagram. Okay, so you have a hot air, which is a forced convection. Okay, compared convection or hot block. So you're going to have a different energy, different different temperature of in the air. Okay, as it is increased, the temperature will be reduced. Okay, as it is elevated to a higher level, so the temperature is going to decrease based on this term. Okay, so we have a forced convection, so we're going to have airflow to the temperature on the level will be at the same, means plus with the velocity towards the air. Okay, now based on Newton's law, cooling, so it's expressed that heat okay, heat transfer rate convection for convection will be in this particular form. Okay, have the A is the heat transfer area, H is the convective heat transfer coefficient, so we're going to have that as well. So surface temperature and also the bulk of fluid temperature away from the surface. Okay, so normally they're going to have a heat transfer coefficient at values for the free convection of gases and liquid. So you're going to have different range for that. So yes, for the radiation heat transfer, okay, we asked previously, due to the electromagnetic radiation, we have a person standing beside the fire, and you can feel the really hot temperature towards the person itself. It's due to the electromagnetic radiation, because when we the electromagnetic radiation due to the infrared region. Okay, so that's why when you use the infrared camera, we can identify whether it's the heat. Okay. So based on the Stephen Boltzmann law, we're going to have it's almost the same with the convection, okay? But it includes the MIT and all the Boltzmann constant. Okay. When you ask me what is emissivity, is actually a ratio of energy radiated from a material surface to the radiated body or black body, something like that. Okay, so you're going to have actual value for that. So for each material, you're going to have different value of emissivity and a constant value. Okay, so this is going to have power of 4 based. The power 4 is due to the experimental work done by Boltzmann, okay, and by Stephen and Boltzmann. Okay, so you're going to have the absolute temperature value for that surface and also the surrounding of the area. Okay, which normally absolute temperature surrounding within 1 meter. Okay. So we have example 2.2. So it's not part overnight open way from large surrounding object. It is desired to know if dew or frost may form on the vehicle tops. Assume the following. Okay, so the convection coefficient, which ambient air to vehicle top is 6. Equivalent sky temperature is negative 18 degrees Celsius. Emissivity of vehicle top is 0.84. Enable conduction from inside vehicle to the top vehicle, so we consider that. So the vehicle tops when the air temperature is 5 degrees Fahrenheit, we can put it as 5 degrees Celsius. Okay, so this formation dew frost occur. Okay. So under the steady state condition, so the energy convected to the vehicle tops is equal to the radiated to energy. So the convection and also radiated heat will be equal to each other. So for the convection will be this in this particular form, and for the radiated top for the night sky is towards here. So maybe we actually, by using this expression, okay, so just substitute towards the formulation. Okay, so what we have here is towards that. So what we have now is actually the this Ti minus T top. Okay, so now you're going to have the equation. So it's written here using the ES software packages, so we can actually calculate this based on the series. Okay, so you're going to have the T top is equivalent negative 3.38 degrees Celsius. Okay, so basically what we have is the water vapor in the air will form frost on the car top. Okay, this also is discussed on the chapter 14, but I just put it there so that you're going to have some idea where to have a look for this kind of discussion. Okay. Now, we're going to have extra problem. For this part, I'm only going to just let you know, okay? We're not going to deep on this as happen towards the energy transfer by work. So for the electric work, so we're going to have the rate of electrical work done by electron crossing the boundary is called electrical power. So the unit is still in watt. So the amount of electrical work done period within a certain length, okay. So or period of time, okay, have the dt. So you're going to have in kilojoule. Okay, so there's two parts. Okay, so rate of electrical work done by the electrons, and the other one work done within a period of time. Okay. No. So mechanical forms of work. So I'll just show it here, but I'm not going to discuss deeply. Okay, because this one, from what I know, is discussed in your mechanics. I think 212. Okay. Okay. Law of thermodynamics. Okay. The first thermodynamics is known as the conversion of energy principle. Like, I still remember the symbol. Like, the flow, as we discussed in the first chapter, related to the internal energy. So we're going to have all the molecules and atoms on the microscopic point of view, and then the conservation of energy. So when we're going to have 100 amount of energy going into the system, it's going to be 100 going out. So the first law of thermodynamics is actually the adiabatic process. Okay, nothing going in, nothing going out. So it's stated between two states in the closed system. So that's it. You can break even law. So this law is a conservation of energy. So going 100, going out also 100. So the energy going in into a system, going to break even, 0. So the condition is going to cross the system boundary of a closed surface. Okay. Now, basically, for the conservation of energy principle for the flow, okay, the total energy coming in minus total energy coming out equivalent to the energy of the system. Okay, so you're going to have the total energy of the system where you include the internal energy, kinetic energy, and also the potential energy. Okay. From there, that's why some of them, if let's say you have changes in terms of energy, that's why you're going to have delta U, okay, to kinetic delta K, and also okay, for the potential energy. Okay, for the moving system, definitely for the kinetic energy, how you get previously on the mv power of 2 over 2 for the velocity, really mass and also the velocity of one particle. Okay, and you perform the integration towards the velocity, so towards the v, integration towards dv, and you're going to have the LV v power of 2 over 2, okay, as divided by 1 plus 1. Okay, so the integration of dz, since dz is not there, so it's equivalent to 1. So when you have the integration towards z, you're going to have z. Okay, use that. Conservation principle system, basically it is written in this particular manner. Okay, so that's why you're going to have it here, delta. Okay. So delta E If it is stationary system, it means when it's stationary system, then you're not going to have the kinetic energy changes or the potential energy changes because it's static. So what we have is actually changes to out of the system, the energy in and out of the system, which involves the internal energy. Okay. This definition for the heat transfer, the work, and the mass flow. So the transfer is energy caused by temperature difference. The work is energy transfer at boundary caused by weight to be raised or not. Okay, and the other is mass flow into the system. Now, so balance for the energy system. Okay, we have for the internal energy. So internal energy, where we focus on the heat transfer. Okay. Sorry. Okay, so this is the general system. Sorry, for the delta E. Okay, for delta E, system equal to the heat transfer plus the work being done plus the flow of mass. So it actually towards the changes of the total energy in the system. To express more on the system, where the system you're going to have internal kinetics, potential, and etc. in that particular system, and the system also have changes of heat, work, and mass. So that is what it's all about. So when we consider in a rate form, so that's why we put it dot over there. Fine. So you're going to have rate of net energy transfer, rate by heat, by work, or by mass. You can also have the rate change in internal kinetic and potential towards the energy. So for constant rate, so you're going to have Q delta T towards the work being done. The rate is W delta T, and for the mass energy transfer rate is also multiplied with the delta T, because you need to have some sort of rate equation towards the calculation. Okay, so basically the energy balance may be expressed on per unit mass basis. Okay, where you have here, okay, it's the same thing, because remember, when you have per unit mass basis, you're actually changing the dimension. You divide it with the mass. Okay. First cycle, like I said, it's adiabatic, so it's a complete cycle where you have the working fluid is 0 for the whole numbers of cycle. So you're going to have Q net minus W net equivalent to delta E cycle. So if, let's say, there's this towards the energy equal to 0, so then you're going to have the heat changes equivalent to the work done throughout the system. Okay, for example, I give you one example. Maybe I have two. Okay, example. So system receive 5 kilojoule of heat transfer and experience a decrease in energy in the amount of 5 kilojoules, in the amount of work done by the system. So we have normally towards the system is one of the easiest example that can be given, because still remember we have the P and so the pressure and volume to a system. So this is what relate with it, when the heat and also the work being done towards the system. So now what we have is the system receive 5 kilojoules and increase in the energy. So decrease energy negative 5 kilojoules. So this is the amount of work done by the system. So energy in minus energy out equivalent to the changes of the total energy system. So you have E in equivalent to K in, where 5 kilojoules, then E out is equivalent to work out, W out. So the delta E will be like negative 5. Okay, so towards the system, okay, out, okay, this particular point, equivalent to E in minus delta E system, W out minus 5 minus. So you're going to have 10 kilojoules of work done by the system. That's why you have a positive value. No, 5 minutes more. Okay, and we have another example, the same example for the steam power plant operates on the thermodynamic cycles towards the turbine. Have a look on this. Okay, so we determine the work done by the steam in the turbine in kilojoules per kilogram. Remember, okay. So when you have that, Q net, okay, W net equivalent to delta E. Okay, for the whole cycle. Okay, so as you can see that the cycle receives 200 kilojoules in the boiler, rejects 1,500 heat to the environment in the condenser. Okay, this part we're going to have like is in a closed condition, so that's why delta equivalent to 0. So Q in minus Q out equivalent to W out minus W in. So you're going to find what is the W out. Okay, see when we need to determine the work done by the steam turbine in kilogram is per unit mass. So that's why we need to identify the W equivalent to W over M, Q over M. So everything, okay. So you're going to have 2,000 minus 1,500 plus 5 on the work cycle. Okay. So you're going to have around this 505 kilo per gram. Okay. So that's it. For example, we have a lot of example actually. Please have a look to it here. Okay. Another part is the energy conservation efficiency. It's more towards the engineering aspect. Okay. It's important to identify what it's all about actually, because measure performance of the device that we have, whether it's efficient or not. So for the refrigerator, we can't have any the COP means the efficiencies of the working compressor is not like 100%. It's going to be like 60%, maybe 50% or 70%. Okay, so the measurement of performance in the device. Okay, so actually the symbol will be in ETA. Okay, ETA, the symbol. So desired result plus the required input. So how will you measure your efficiency in the thermodynamic cost? Okay, so basically you need to have the working fluid undergoes a serial process and return to original state. So the process of the system and the cycle is it as it begins or not. So that you have the heat engine. Okay, so let's say a system in a system. So for the boiler, the turbine, the condenser, and the pump, refrigerator system or steam power plant. Okay, so you're going to have a system in a system. So these are system boundaries. So the work being coming in from here. So coming in, heat going out from the condenser coming into the boiler because it's a boiler. So more of energy coming in, so there is more of heat coming in to the turbine. So from the pump, from here towards the boiler, up towards the turbine, is going to work the turbine, so the power is going out, and rest will towards the condenser, means the fluid going back towards the condenser, and you have the energy thing in terms of heat. Okay, go out from the condenser. That's why you when you're near to the condenser is like very hot, something like that. Okay, so basically here we have the steam power plant. Okay, so basically we have certain efficiencies value. Okay, so more efficiencies, the inner performance for work produced devices. A heat engine is defined by the ratio of the network output towards the heat input. So you have desired result and the required input. Okay, so basically when you have heat engine, you need to identify the network done. So desired result is the work. Okay. The required input is the heat coming in. So then you're going to have the thermal efficiencies, and it is always less than 1 or than 100% if let's say you're going to have it in percentage. Okay. So that's it. So to you the example. So how is done? Okay. In example 5, we're going to have steam power plant receive 2000 kilojoules and 5 kilo of pound work and produce like 505 kilos per kilogram of turbine work, and determine the thermal efficiencies of this cycle. So basically the work net out and heat transfer in towards the mass per unit mass is considered in this part. So then we perform the calculation, we just have 25% efficiencies. Okay, and that is under combined efficiencies, or is part of the combustion chamber. So it's because in system we can calculate the efficiencies value, but bear in mind what is from the output of the system. So that's it. Because my point is until here only, like the thermal efficiency. The rest will not be fully discussed. Okay, it's the lower heating value. Okay, I just give it to you combustion part. Okay, so with that we also have generator efficiencies, like plan overall efficiencies. So this when we go towards more deep towards the power plant. Okay, and now we're going to have like lighting efficacy, means the efficiency of the light lumens. Okay, so we got amount of light in lumens and watt of electricity consumed. Okay, so we're going to have light efficacy, and also for some cooking in, okay, useful energy transfer to food and energy consumed by the appliance. So you can save your money or not after that. So that's it from me. So sorry about as I exceed 15. Okay, so I already upload the notes in the e-learnings. Please have a look, and you can always email me, okay, with anything that you want to know. That's it. Okay, for now. Okay.